Okay, so today we started talking about E, which is equal to about 2.71828, blah, blah, blah. And we started to talk about some random places where it shows up. The most intuitive way to think about it is in compound interest problems. So we did the limit as n approaches infinity of 1 plus 1 over n to the n power. So basically the idea here is we have 100% interest, which is this one here, and we're compounding it n times, right? So if we compound it n times, we have to apply our interest n times. So the idea here was, as we compounded more and more frequently as n approached infinity, this limit approached e. So e is the result of continuously compounding. So where this shows up in nature is like population. So the more people there are in a population, the quicker the population grows. The growth rate of the population directly depends on how many people are actually there and reproducing. It's the same idea with radioactive decay. So as an isotope decays in chemistry, the bigger the object is, the quicker it decays. But as it gets smaller and smaller and smaller, it decays at a slower and slower rate. So the function involving E, when we model exponential growth or decay, is P of t equals P naught, which is our starting amount. Then we bring in our base of E, raised to an exponent. And what this exponent is determines how quickly the thing is increasing or decreasing. So K is either our growth or our decay factor, right? If K is positive, we have an increasing function. If K is negative, we have a decreasing function, okay? And if K is larger, we're going to be increasing quicker, or we're going to be decreasing quicker. And then T will always be some type of unit of time. So for example, we dealt with a population of 2,000. Okay, that population is growing, and we model it by saying 2,000 times e to the, we said 0.02, we just said it had a growth factor of 0.02 times time. Okay, this function will tell us the size of the population, in this case, after a certain amount of time. And again, as time goes on, this population is going to grow quicker and quicker and quicker because it has more people to reproduce. And so over time, we just model it with an exponential situation. Now in finance, though, oftentimes the amount is not compounded continuously. It's compounded a certain number of times. So in this example, we're compounding quarterly in a year, which means we're compounding 4 times. So this represents a starting amount of $300. Okay, we're getting 16% interest compounded quarterly. So if we're compounding it quarterly, we have to apply our interest 4 times. So we can actually simplify this to get a better idea of how this looks. We get P of t equals 300 times, well, 16%, 0.16 divided by 4 is going to be 4%, right? 0.04. 0.04. So what we end up with is 1.04 raised to the 4t. Okay? So this means every quarter we're getting 104% of our money. And that happens every quarter, and then at the end of the year we're going to get a total of 16% interest just split up into those 4 quarters. So let's look at one given year. We have $300. In the first quarter, we get 104% of our money, which means we're gaining 4% interest. And then we're going to get 104% of that, and then 104% of that, 1.04 again, and then 104% of that. Okay, so let's actually see what values we end up with here. So after 1 quarter, we now have $312. Okay, multiplied by 1.04. Okay, so now we have to multiply our 312 by 1.04. This is in the second quarter now that we're compounding again. So we do 312 times 1.04. And now we have $324. 48 cents, right? And now we have 2 more quarters remaining, so we're going to multiply by 1.04 2 more times, and I'm just going to do both of these at the same time now for time purposes. So at the end of the year, we turn our $300 and we end up with $350.96 about, so $350.96. Okay, so we can see how if we had just applied, we can now see how if we had just applied our 16% interest as one lump sum, so if we did 300 times 1.16. We're just going to gain our 16% interest right away instead of compounding it. We can see the difference. Oops. We end up with $348. Okay, so it really only ends up being a difference of what, about $2, $3, $2.96. But you know, that's not nothing. And as your money, if you have more money, that difference is going to be more important, right? So the more times you compound, you end up getting more money. But it does have a limit. Remember, as we compound continuously, we end up using a base of E, which is what we did with our populations.